In Lecture 30, we're going to be looking at the complex plane. In order to talk about the complex plane, we need to recall the arithmetic of complex numbers being those numbers that involve the imaginary unit, I, which is the square root of -1. That concept of an imaginary number would have been introduced in an earlier course in either college algebra or an earlier algebra course. Once we recall what we mean by complex numbers, we'll then talk about a way of representing complex numbers on the complex plane. By introducing the coordinates of a point on the complex plane, we will then be able to draw a connection between both our polar coordinate system and our rectangular coordinate system, which involves trigonometric functions. So in this section, we'll do a review to begin with of the concept of a complex number. To start off with, let's recall that the imaginary unit is the number which satisfies the equation x squared is equal to -1. Now, you'll recognize that there is no real number that actually solves that, real being the operative word, because if I were to take -1 and square it, I get +1. If I take a +1 and square it, I get +1. So the question is, what can I square to get a -1? And the answer is nothing in the real number system. So we introduce a new number, which is not a real number. Real being a defined concept in mathematics, a set of numbers that can be represented as a decimal number. But this is not a real number. This is a new type of number that will help us to solve new types of problems. So we're going to call that number I. And the way that we work with I is to think of it as the way of taking square roots of negative numbers. Since I can rewrite square root of -4 as the square root of -1 times 4, I'll think of this as square root of 4 times square root of -1, which is 2, because that's the square root of 4, and I, which is the square root of -1. So the square root of -4 is 2i. And the easiest way to think about this I is to think of anytime you have a negative inside of a square root, you can pull it outside and think of it as I. So in this case, the square root of 8, which is negative, is the same thing as I times the square root of 8, which I can then simplify my 8 into 4 times 2 and get the square root of 4 times the square root of 2. And knowing that the square root of 4 is 2, I end up with a 2 out front, an I out front, and a square root of 2 inside. So 2i square roots of 2, or if it's easier to think of it, we can write it 2 square roots of 2 times I, right? That's a real number times I. We prefer to write things out in front of a radical so there's no confusion about it being inside or outside of the radical. But square root of a -8 is 2i square roots of 2. And so a complex number is going to be any number that involves that imaginary unit in the following form. That is, it's a number that is a real number A plus a real number B times I, A plus BI. So if we have a number, if we call it Z, and that is in the form A plus BI, a number plus a number times I, we call the number A the real part of that number, that complex number Z. And we call the real number B, which is the number that's out in front of the I, the imaginary part of that imaginary part of Z, which we denote by IM of Z, and RE of Z is the real part. So the real part of Z in example A is 3, and the imaginary part of Z is 2. Not 2i, it's the number that's out in front of the I as the imaginary part, okay? In B, example B, the real part of Z there would be the number without the I, so it's just the number 2. The imaginary part of Z would be the number that's times the I. So everything that's times the I, sign included, radicals included, so everything that's times an I would be a -2 square roots of 2. The real part on example C is in fact 0, because there is no number explicitly written, but we can think of this as 0 plus 4i, since that's the same thing as just 4i. Therefore, the real part, the part without an I in it, is 0, and the imaginary part would be then 4. On the last one, thinking about it in almost the exact same way, only realizing now that this doesn't have any i's in it at all, this is in fact just a real number. This could be thought of as negative 8 plus a 0i. So the real part is negative 8, and the imaginary part would be 0. Note, any complex number with a 0 imaginary part is a real number. It's just a fancy way of saying all real numbers are in fact complex numbers. Complex numbers is now an all-encompassing set that covers all types of numbers that we've ever seen before. To add or subtract complex numbers is actually fairly simple if you just think of it in terms of this as binomials. Even though I is not a variable, I is a number, you can still think of it as a coefficient times I, in that case an imaginary part times I, and you will collect like terms. So anything with an I you will add together, anything without an I you add together. So first of all, in order to do that, make sure that your complex number is written in a plus bi form, which would mean if you have any square roots of negative numbers, be sure you rewrite it so that it has an I instead of just negatives under the square root. But once you get it into a plus bi form, then add or subtract the real parts, since those are alike, those are like terms, and then add or subtract the imaginary parts, since those are also like terms. So it's just like the technique to collect like terms. And then leave your final answer in a plus bi form. So it's relatively simple if you think about this example. It's because there's a plus inside these two complex numbers, we can simply eliminate the parentheses and write this as 2 plus 4i plus a negative 1 plus 6i. So we'll group the real parts together and we'll group the imaginary parts together. So a 2 plus a negative 1 is a negative 1, and a 4i plus a 6i is a 10i. That is how we would add two complex numbers together. You start with two complex numbers, add them together, the answer is going to be a complex number. Subtracting is similar, except the first thing you got to remember is to distribute the minus sign. We could rewrite this as 3 plus I minus 1, because minus times a positive 1 is a minus 1. Minus times a minus is plus 2i. And now collect the real parts and the imaginary parts. So 3 minus 1 is 2, and I plus 2i is 3i. That's a plus bi form, so that is our final answer. Multiplying complex numbers is also very much like a technique that we've covered in working with binomials. You again, just as with the adding and subtracting case, start by writing both of your complex numbers in a plus bi form, and then distribute. And by distribute, you can think of that as the FOIL technique that you use for binomials. Remember, if you have a plus b times c plus d, you can multiply the first, the outside, the inside, and then the lasts together. Well, if you had an I in here and an I in here, so it's a plus bi and c plus di, you would do the same thing. But there's one caveat, one extra rule to remember. When you multiply the lasts together, you end up with the last term being a b times a d, whatever's there, and an I squared. And that's the part that you got to be careful of. Because what is, in fact, I squared? So I'm going to scroll back up here and remind you that the definition of the imaginary number right here and right here is that it is the number that when you square it gives you -1. That's what I means by definition. So when you then come back down here and you see an I squared, guess what? Since I is the number that when you square it gives you -1, this right here becomes a negative BD. So I squared always becomes -1. So you see that in my note that I've written right here. We're going to use I squared equals -1 to simplify. And then for number 4, the last step should not be number 1, should be number 4. simplify, which means to collect like terms again. All right, so you FOIL, but then you remembered, anytime you see an I squared, it's -1. Replace it with -1. So let's try that. Let's FOIL. So first, 4 times -1 is 4. 4 times a minus 4i is -16i. The inside is going to be a -3i, because that's 3i times -1. And then the last gives me a -12i squared. And remember, I squared, I'm just going to mark it out and replace it with a -1. So what do I have? I have -4 minus 16i minus 3i minus 12 times -1. But minus 12 times a -1 becomes a plus 12. So that's -4 minus 16i minus 3i plus 12. And now we collect the like terms together, and we end up with a -4 plus 12 is 8. And a -16 minus 3, all times I, would be -19i. 8 minus 19i is the product of those two complex numbers. We multiply two complex numbers together, we get a complex number as an answer. So we have done addition, subtraction, and multiplication. Division is actually nothing like what we cover in our early algebra days. It's actually more like something we've covered much later in college algebra when we start talking about rationalizing denominators. Because when you divide by things that involve I, you are basically dividing by something with a radical in it. Because I is the square root of -1. It's like a radical. So you have to recall that there's a technique to get rid of radicals in the denominator when they're involved in a binomial form. So we're going to get to that. But in order to talk about that, we need to recall a word that we've used in our mathematics classes before. We're talking about it again here. It's the concept of the conjugate. And in this context, we're talking about complex conjugates. It's actually a relatively simple concept because by definition, all we mean is that if z is a plus bi, and that's a complex number, then its conjugate, C-O-N-J-U-G-A-T-E, conjugate, is denoted by z bar. That is a bar over the top of z, which you can read as z bar or z conjugate. So z bar would be the conjugate of a plus bi, and guess what its definition is? Here's the definition. It's a minus bi. Change the middle sign and you've got the conjugate. So for example, on number A, or letter A, 3 minus 2i, the conjugate is 3 plus 2i. If you have 9 plus 2i square roots of 2, its conjugate would be 9 minus 2i square roots of 2. When you have only single terms, you just have to make sure you recognize what's the real part and what's the imaginary part. For 8i, this is 0 plus 8i, which makes the conjugate 0 minus 8i, or a -8i. Maybe it's even easier to just think of conjugates of complex numbers as changing the sign of the imaginary part. That's all we mean by the conjugate, is to change the sign of the imaginary part. Which would mean if I have 9, that's the same thing as 9 plus 0i. Its conjugate would be 9 minus 0i. Or 9 minus 0 is still 9. The conjugate of a real number is itself. Note, let's write that down. The complex conjugate, let's do ATE. Let's write that a little bit neater. The complex conjugate of a real number is itself. And that's only true for for real numbers. Real numbers are the only type of number whose complex conjugate is itself. But that's something you can say about all real numbers. So then let's write down a theorem that has to do with what happens if you take a number times its complex conjugate. The product of a complex number and its conjugate number is always a positive real number. And here's why. If you want to multiply z times z bar, think about what that is. If z is a plus bi, just rewriting z there. What is z bar? Z bar is a minus bi. Correct? And now, if you multiply these things out, you get a squared minus abi plus abi, that's outside and inside, minus a b squared I squared. Correct? Now, the middle terms of these two, of this product will cancel each other out because they're the same, only opposite signs added together. So you end up with an a squared minus a b squared I squared. But what is I squared? I squared is a negative 1. So if you have a squared minus b squared times a negative 1, that's a squared plus b squared. And looking at that, how do you know that that is a positive real number? You know it's real because a was real and b was real, right? That's what's always true up here in the definition of a complex number. So a is real, b is real, and if you square a real number, you get a positive number. If you square a real number, you get a positive number. So a positive number plus a positive number is going to be a positive number. So I can claim without a doubt that that is always going to be positive. So if you take a complex number times its conjugate, it's no longer complex. You get a real number as an answer, and in fact, a positive real number. To do division of complex numbers, we will use that notion of the complex conjugate and the previous theorem that says multiplying by its conjugate gives you a real number. So we are going to multiply the numerator and denominator by the complex conjugate of the denominator. And it's fairly easy to see why if you look at an example. Consider 1 plus 4i divided by 3 plus I. We want to know from this question, this is actually asking, what do I have to multiply 1 plus 4i by so that when I work it all the way out, I get 3 plus I? That's what I want to find the answer to, is what goes here in the question mark. And even though it doesn't seem obvious, we are going to be able to get there by multiplying by the complex conjugate of the denominator. I think once you see it worked out, you'll see why we can get the answer once we go through this process. So what is the conjugate of the denominator? It's 3 minus I, and 3 minus I on top. So multiplying out on top and bottom. Remember, on bottom, you're going to get 3 squared plus 1 squared. And if you need to multiply it out by 4, you can, or you could simply use the theorem that we just covered on the previous page. But you take first plus the outside plus the inside plus the last. The outside and the inside will subtract out, and the last becomes a negative I squared, which is a plus 1 squared. On top, we actually do have to FOIL. So on top, I'll take 1 times 3 and get 3. And then 1 times a minus I is minus I. 4i times 3 is plus 12i. And then plus 4i times a minus I is minus 4i squared, which gives me a plus 4 then, because I squared is negative 1 and it changes the sign. So you end up with a 7 plus 11i divided by 10, because that's 9 and that's 1. And when you have a binomial over a single term, you can rewrite it in terms of two fractions added together, 7 tenths plus 11 tenths times I. And I like to write it in that form because that's a plus bi form. You have found the a and the b, so that if you were to plug that in right here and multiply it out, you would get 3 plus I. You have found the answer to the division problem. But the way you got there was by multiplying by the conjugate of the denominator. I do prefer you to go ahead and rewrite this thing out in terms of a real number plus a real number times I, or a plus bi form, even though technically this is also correct. On example B, we just have to remember on bottom we have a 0 plus I, so that the conjugate now is a 0 minus I, or just a minus I on top and a minus I on bottom, to multiply by the conjugate of the denominator. On top, that gives me a minus 2I minus I squared by distributing. And on bottom, I get a minus I squared. Remembering I squared is negative 1, that gives me a minus 2I plus 1. And on bottom, I have a 1. So really, this is just 1 minus 2I. That's the answer to that division problem. The complex plane is a concept of taking the complex number form, a plus bi, and thinking of it not in terms of a and b, but as being that it's a real number plus a real number times I. Let's think of each number as a point where the real part is a value corresponding to a real number axis, and that the imaginary part, the y in my case, would be a number corresponding with a vertical number line or imaginary axis. So every complex number, x plus yi, can be thought of geometrically as a point on some plane, which we'll call the complex plane. So, for example, if I said 3 plus 2i, that would mean go over 3 and up 2, and you've got some point. If I said negative 2 plus 1i, that would be over 2 to the left and up 1. So points now have a location. Complex numbers now have a location on the complex plane. Now, this x and y are thought of in terms of their rectangular coordinates on this complex plane. But if we think of the point in terms of its polar coordinates, we give a special name to the r and to the theta. That would be the polar coordinates of a given complex number. We call the distance from the origin the magnitude, or sometimes it's called the modulus of a complex number, and it's denoted by the same symbol we used for absolute value when we talk about real numbers, which makes perfect sense because you'll remember, hopefully, that the absolute value of a number, a real number, is how far it is from 0. Like negative 2 is 2 away from 0, positive 7 is 7 away from 0. Well, when we're talking about complex numbers, we're going to be somewhere in the plane, like up here. We have some distance away from 0. We're going to call that the modulus of z, or the magnitude of z. And we can find it using the same formula we used for the radius, or the r, in our polar coordinate system. Okay, so it's defined as the distance from the origin. Now, in upcoming lectures, we're going to talk then also about where the theta would lie. And I don't know why I left it off, but I'm going to go ahead and stick it in here. I don't think it's anywhere in your homework, but this theta right here, the theta for the polar coordinates, or I should say of the polar coordinates for the complex number x plus yi is called the argument of z. All right, so we'll talk more about the argument and the modulus in upcoming lectures.